All right, now let me tell you this. The equations for the actual characteristic impedance on a piece of Duroid board, I'm not worried about that. Right? Really, I'm not. And right now, everybody's got just, if you want a certain line width and a certain impedance, whatever the constraints are, you type them in, and literally it's taken care of by the lithography methods that they have. So I don't worry about that. But what you have to understand is this. When we have a Duroid board, or any of these FR4 where we have it's copper clad, what we're going to do is put patterns on there and etch off all the copper except the copper we want to make the transmission line connections to the different pieces, to the antennas, to the power amplifiers, to the ASIC chips. When we're doing this, almost always, not always, but most of the time, we're talking about things that are greater than a tenth of a wavelength long, so they are transmission lines. They're high frequency components, they're transmission lines. I wanted to bring a piece of Duroid board in. I ended up tied up with something, but I'll bring it down on Monday to show you, and I'll show you even, if I can, some things mounted on there. A lot of you in this room will be working with this kind of stuff. You'll be doing this. It's things where you build real devices, get them to the market, and it's something that, have you all seen either Duroid board or FR4 and worked with it? How many have? Did you work with it in a laboratory or not? I don't know if you get a lab with that. Most of your labs are just breadboarding, I think, these days, right? You don't have to fab anything. Hopefully by the time you're seniors, at your senior design at least, some of you will be exposed to this because it's real important. I did a senior design years ago where I had groups of students build antenna arrays, and they fed them, and they used Duroid board to do this. They fed them to obtain certain patterns. It was a very interesting project because what you don't know is how creative some students are, because they're not told they can't do it a certain way. So they actually go after designs that are very unconventional, but they work. And that's the one thing that I like to see, and it also exposed them to Duroid board and the fabrication. I don't know who's doing the lithography now. We used to have Joe Haggerty, but he retired. I'm not sure if Mike Eddy will do that, but I'm going to ask him just in case I get a shot at a senior design. I might try it. All right, now today, what I'm going to tell you is what the part of this I'm going to talk about next is doing impedance matching using microstrips, using things where basically we have a characteristic impedance, we're going to do impedance matching, but we're going to do this in an odd way. Instead of having, before, how did we impedance match anything? Well, what we either did is shunt or series stub tuning, and we let the stub go a certain length, right? Y'all remember that class? Now that's fine, that'll do it. But a lot of times stub tuning, when you have a long piece, that's a big piece of footprint, they call it, off of a piece of Duroid board. So what they'll do is try to put an actual component, like a capacitor, small capacitor, and sometimes even a small inductor, even though inductors are rare. Thank you. All right, I'll get to it. I'll get to it later. All right, that's okay. Oh, I know why. Anyway, what they'll do is usually use capacitors if possible, and rarely inductors, and I'll tell you why. Inductors are miserable little things because they give a lot of field, electric field, magnetic field in the vicinity. Capacitors don't. They're contained pretty much. So just remember that if you're ever given a choice between one or the other. The thing about inductors are they are used a great deal for something called pi filters at low frequencies to get rid of the high frequency actuals, or really the 60 hertz ripple. And that's something, so you do use them. Now, back to this. I put something on there today that was a rotated Smith chart. Has anybody seen it on? You have? If you look there, it's a rotated Smith chart. What I want you to do is follow me here. This is all about using impedance matching with rotated Smith chart. And I don't want, I used to make people bring in their Smith chart right now and do this. I want to go through this part of the lecture just up here so we can talk about the reasons for things, all right? So if you have a Smith chart, a standard Smith chart, it looks like this, right? And you're going to have a center point here. That's key. And then you're going to have something called the one circle. That's R equal 1, and that's the important part. Then you're going to have a couple of identifying points. Here, you're going to have 0, and it'll also be the point for when you have the outer part is wavelengths towards generator. That is the 0 point there. that you actually start measuring. Everything is in fractions of a wavelength. So you take whatever length it is that we're going to be talking about and divide that by fractions of the wavelength. Now, I think most of you appreciate what I'm talking about. When you do this, this point right here has a value of infinity in the impedance domain. And it also is at a distance of 0.25 lambda, if you want to put lambda in there. Now, this point is J1. I call it the North Pole. This point is minus J2. And all the rest of it fills itself in this manner, just so you get a handle on the Smith chart if you don't remember it. There will be concentric circles that will have their edge here that are symmetric about the horizontal axis. These are just real circles. This would be like r equal 2. The tighter they are, the larger the value of r. Then this one right here, the big one, is r equals 0. That's the outer rim. You also have things where you'll have lines like this, and they represent values that are plus or minus j something. The center of these circles is out here. This would be a J1. A J2 would look like this. And I think, I'm just refreshing your memory. This would be a minus J, this would be J1 here, pardon me. This would be like minus J2. Are we clear on this? Just to refresh your memories, how a Smith chart goes about doing its business. So if we take a load, and I'll try to do it this way. Matter of fact, in your book, I don't know if I brought mine or not. I didn't, but if you look in your book, this is L section matching, because I know some of you do bring your book, and these are the scattering parameters. We're doing matching right now, so this is on page 553, and I'm going to start with the one. Yeah, we're going to start 552 and 53. Now, let me go through this. So first one is we're going to have ZL, all right? Then we're going to have Z naught. Now, this is your standard beginning point, right? Well, the first thing you always do when you do matching is divide ZL by Z naught. You need a normalized value. So step one, take, and we'll call this small ZL, and that's capital ZL, the load, over Z naught, right? So, for instance, if ZL here, I'm just going to make up a number. Suppose it was 200 plus J100, and say Z naught was 100, just so we see. Then the normalized value here of ZL would be equal to 2 plus J1. Does everybody follow me on this? All right, now, typically you locate that point, right? So when you locate that point, you're going to see that this point, and this is the important thing, for condition A is ZL is inside the one circle. Let me show you what I mean by that. If you have an impedance that lies inside the one circle, there's the one circle. If it's inside it, either here or here, anywhere, inside there, you use this method. Now, I'll explain why. And I want you to listen, and it'll make sense, too. If I look at that one that I chose, it's 2 plus J1. Well, 2 is inside, right? Do you agree with me? You follow me on this? The real part is 2. That would be about there. Do you all see this, class? How many see this? Can you all see it in the back of the room? I worry about you. Allie, can you see it where you are? The 2 circle is about here. This is the 1 circle, goes right through the center. 2 circles about here. Do you see it? Now, 2 plus J1, just, I'll just, say this is 0.1. It's really going to be, this is the normalized ZL. And I always tell people to label their points and circle it. That's the first point, right? Now, I want you to understand something. If we were going to add a series element first, we would like to add a series element that does 2 things. First, it would get rid of, in this case, the imaginary part, the J1, which we could put a minus J1 inductor in there, right? I mean, capacitor. Do you follow me on this, class? But no matter what we did, we could not reduce that value of 2. You can't add negative resistance. So we're stuck where no matter what we do, we would be inside here. And the goal is to get the real part to be 1. With any kind of impedance matching, I don't know if they told you this, with either Y or Z, you want the real part of either to be 1, and then your problem's basically solved. Do you all follow me on this, class? Because if it's 1 and you get rid of the imaginary part, the normalized, remember that's normalized, that means now the impedance times the normalized impedance, whatever that value is, 1 times Z naught is Z naught. Now you're looking into Z naught, so your reflection coefficient's 0, and that's the goal of impedance matching. You want nothing reflected. You follow me on this, just work with me, you'll see why. No matter what we add in series, it doesn't work. So we have to go to the admittance domain. So follow me on this. This does not work here. So what I'm going to do, if I go to the admittance domain, we add admittances in parallel. So this is the first point. Now because it's inside the 1 circle, you come and you literally, there's a rotated circle. If you look where I showed you, there's a rotated circle right there on the other side that's exactly symmetric, and he shows this on page, what is it? 552 and 553, I think, and probably a few other pages. If you look there, you'll see this with me. Now, I come and literally, I get the conjugate point. I come right through here. If that's ZL, this would be YL. And it's just 1 over ZL. And it's really, if you take a line, draw it, or take your ruler and go from a point right there through the dead center of the circle, and you could take your, your compass or anything like that and measure the distance. It's symmetrically on the other side. Follow me? This is YL. This is point 2. Now you're in the admittance domain. We're going to add admittances in parallel, right? Add impedances in series if we want to add them up, right? Does everybody follow me on this? All right. Now, we have 2 choices. In the admittance domain, and I better do this, if we have a capacitor, the symbol for a capacitor is this, or if we have inductor, symbol for inductor is this. If we look at this, in the impedance domain, the Z domain, the capacitive impedance is minus J over omega C. The impedance has an impedance of an inductor is just J omega L. Do you all follow me on that? Now, everything's normalized. So normally when we normalize in the impedance domain, we divide by Z naught. Just keep that in mind. Now that's the impedance domain. This is for the capacitor, normalized, and that's the inductor. You'll notice they're both positive values. Everybody follow me in this class? That's a positive impedance. That's a minus impedance. This is positive, but that's minus. And they're both functions of omega. Omega L it's directly proportional to omega. 1 over J omega C is inversely proportional. Now, that's normalized too. Now, in the Y domain, what happens is, well, we just flip this. Do you follow me? So in the Y domain, we would get plus J, right, times omega C Z naught. Over here, we would get minus J times Z naught over omega L. Now, the reason I normalize these is because everything we do when we're dealing with any kind of matching on a transmission line assumes normalization of the impedances or the admittances. How many understand that right there? Have to do it that way, but if you listen to me, you'll understand. Now, I have 2 choices when I'm here. This value, can somebody does anybody have a calculator out? Just take 2 plus J1 1 over and give me this exact value right here. Take 1 over that, just 2 plus J1 and take 1 over. I just need the inverse. I need Y. That's what I need. 0.4 minus J 0.2 is equal to really YL. It's 1 over ZL. Do you all follow me? Please listen now. I want to make sure everybody understands this. I want to make sure I got everybody's attention here. All right, now watch. This is the real part, right? Now that real part means that somewhere out here, there's going to be, and I didn't draw that very well, but there's going to be a 0.4 value, all right? Now listen to me carefully here. If I added positive J something, right, which would be like adding a capacitor, I could move this way, and I could get to the point right here where the 0.4 intersects this rotated circle. Can everybody see that, class? That's going positive. Or I could add negative values, and this still would be at the 0.4, real part 0.4. Can't do anything with the real part until I hit this point. Do you follow me? Now, if I chose to go this way, this is 0.2, this would be 0.3. Can somebody look at that Smith chart in the book, or if you could look at my Smith chart that I sent there that is on OneNote. Anybody have OneNote up right now with that? If you could look there, look at the value of 0.4 for the real part and see where it intersects the rotated circle. It'll give me a value of real and imaginary point right there. Anybody? No? No, you won't get it there. Can you see it, anybody? Here. I was hoping. You don't have it. Here. All right. See, this. Well, there's 0.2, there's 0.4, right? But you're going the wrong way. It's over there. 0.4. So if you look, can you get this where this? It's hard for me to see this, but right there, and you got to shrink that a little because I need the imaginary part. So go from 0.4 right there. Can you go down and it's right there? What is that? The imaginary part is 0.5, I think.
Yeah, 0.5.
All right. So here, bear with me now. We started here. We can't do anything there. We can't add anything in series that'll get us anywhere. So we go to the admittance domain. We're here. That's where we land. Now we're going to go to here. Follow me? This value right here of y, remember we're in the y domain, is going to be 0.4 plus j 0.5. That's the y value right there. Do you all see this, class? Follow me? Now, how much did I have to add to get there? Well, I started at minus j.2, right? I had to add what? I had to add j.7 to go from here to here. So that means from here to here, when I'm going there, I'm adding plus j 0.7. I'm adding that, which means that in parallel now, if I choose to go that way, I'm going to have a value right here of, and I'm going to realize this in a second, of j 0.7. Follow me? Remember, it's the admittance domain. Do you all see that? I'm going to take you through every kind of permutation of this so we can talk our way through it. And I really don't want people to spend a lot of time on Smith charts just looking at the intent, trying to split hairs with the things. I want you to see the actual principles at work. All right, now when I get here, at this point, I add this plus this, right? You all agree with that? And what am I going to have? I'm going to have, at this point, I'm going to have a value of y equal to what? It's going to be 0.4, right? Here, it was still 0.4 plus j.5, right? You follow me? Plus j.5. Now, here's why I want that. And some of you see it. Because I know that this point has got a conjugate point right through the center of the circle here. Do you all see that? And that has the real part of 1. Follow me? If the real part is 1, now I add a second element to get rid of the imaginary part in the impedance domain. Does everybody follow me on this? I'm going to walk you through it again. All right, the whole goal of this is we want to land right here, dead center. When all is said and done, we want to be in the dead center after we add elements, right? So the first thing we had to do, the way we did this, because we're right at the load, we go to here, we haven't moved anywhere yet, and we see we have to add a certain amount of admittance. We have to add j.7 to get to this point, right? By adding it, now I'm at this point, 0.4 plus j.5 right here. If you've got a calculator, do this. Now, take 1 over that. Now we're going to go from the admittance domain back to the impedance domain, and this is going to be the 4th point. And you should get about 1 plus j, or minus j something.
0.976 minus 1.22.
All right, so now the impedance of this right there is, you said 0.97? 97, it should be 1, so we're going to do an approximation minus J what? 1.22. Anybody confirm that? About?
Yes.
All right, you got it? All right, now we're right here, and we're in the impedance domain, right? All right, now listen. This is the one time you're going to actually use an inductor. To go from here to here, what do we have to add in series? We're in the impedance domain, they add in series. It would be an inductor with a normalized value of J 1.22. Do you all see this? So what happens is, we'll get to that capacitance value. Right here, I'm going to have now an impedance, right? And I'm going to tell you what these values are. And this impedance is going to be, this is the Y right here. This is Z, and this is impedance is J 1.22. Are you with me? Now, if we did this right, then from here on, what we're going to have is a Z in equal to Z naught, and that means the reflection coefficient right there will be equal to 0, about 0. Can you all see this? And here you notice the beautiful thing is we didn't move down the line anyplace. The only thing we did right at where that load is, we inserted a capacitor in parallel. And then right there, we inserted a small inductor. Do you all see this, class? So now we're going to calculate what that capacitor is next. I did it this way for a reason, because you can see we're now adding, we're going to take this, normalize it. The real part's too big. It's inside the one circle, so we go to the admittance domain. In the admittance domain, we want to move to the rim of that rotated circle. By moving to the rim, we add this as a normalized capacitive reactance. Now we're on the rim, and then we go back to the impedance domain, and we add in series an inductor to get rid of that minus J 1.2. So what's the value of this capacitor? Well, if you look at this, and I left it normalized here, in the Y domain, the normalized capacitive reactance, or capacitive admittance, is omega C Z naught. So we take, and you can take this to be anything you want, but we can take omega C Z naught is equal to, in that case, 0.7. Do you all follow me in this? I got rid of the J. Class, are you with me? Can you all see it over there? I got to make sure. Back there? All right. All right, now, what's given, what's not? Z naught's given, so we're going to say that C would be equal to 0.7 over omega Z naught. So that means whatever omega is and Z naught, they control the value of C. That's the value of C. Got it? I want to do some of these too. The next thing we're going to do is calculate the value of L. Well, here, this is an admittance, right? The next one's an impedance. Well, the impedance right here is going to be J omega L over Z naught, or really just omega L over Z naught, would be equal to 1.22. Can you follow me on this? So that's equal to 1.22. And that means L is equal to 1.22 times Z naught over omega. That would be L, and that would be C. And this is the first one in this, the whole thing for this one that I'm talking about. This is all based on if ZL is inside the one circle. These are the steps you take. If it's inside the one circle, no matter what I add to that in series will never get me to a point where I've got 1 plus J something. All right? It's always going to be larger than 1, so you're always going to be stuck inside no matter what you do. And you're going to be in that loop no matter what you do. So you have to go to the admittance domain. And then in the admittance domain, you're inside the rotated circle. Remember that? And now you're going to add admittance until you get to the rim. One thing I didn't say, I could have gone this way in the admittance domain. And that would have been adding an inductor. You follow me? Instead of a capacitor in parallel. And then when I came here, I would put a capacitor in series. So either one of those two. Usually I tell people, put the capacitor in parallel. Just me. All right? It usually works better. Inductors in parallel have one big problem. If there's any resident DC voltage, like driving a gate or something like that, they're shorts. So inductors are short circuits at DC. You got to keep that in mind whenever you're doing circuit design. Because you know, when you had, I think you had your, you had a standard microelectronics like FET and BJT designs for circuitry. You know, with the offset bias on the BJTs, right? You had to have some current through there. Well, if you use an inductor in parallel with that gate, if this was going to be a high-frequency circuit that you were driving, it shorts it out. Right? And you don't want that. It just takes the gate to zero DC-wise. So remember, inductors are best in series, capacitors always in parallel. Remember that, and you'll be safe. Did you have a question?
Yeah, would the inductor value be negative C naught over
Would be what?
the inductor value that you have? Would it be equal once at negative C?
No, this is it. It's omega L over, like think of, what's the impedance of an inductor? J omega L, right? We were trying to add a positive impedance because this is negative back here, right? So the inductors is J omega L normalized divided by Z naught, right? That's all you got to do. All right, this is the first step. Now the second step, all right? Are you with me? I'm going to erase it all. Remember, if it's inside the rotated, you got to go to the other side. Now, the next part, and this is, you can almost guess what this is going to be. First one was, after the normalized impedance was inside the one circle. I don't know if Dr. Wentworth's book follows this, but I think it does. So now we do part two, and I erased everything. So now let me put the Smith chart up there. This is J1. This is minus J1. This is infinity. This is 0. And this is the one circle. And this is the rotated one circle. So that's R equal 1, and this is the rotated circle. With me on this? Just try your best to draw it. I'm not very good at this, but I think everybody can at least sketch the general idea. Now, part 2, or part B. Now, ZL is inside rotated circle. All right, so I'm going to go ahead and I'm going to try to come up with a problem that'll do this. Hopefully I can. So I'm going to have Z naught here, B at 100. And I know that I've got a value of 0.5 about here. I'm not very good at this, but this is about 0.5. That's the real circle of 0.5. Just take a look at, try to draw that. And here, I want something inside. Now, tell me if I'm wrong here. Isn't the value of 0.5 plus J.25 inside there? Could you look and see? The imaginary part is J.25. I'm not actually sure. Let's go J.2. That'll pull it in. It's going to be right in there. Can you all see that one? How many can see it's inside the rotated circle? Please take a careful look. I want to make sure it is. Is it? All right. Now, it's inside the rotated circle. So this is 0.1, and it's going to be 0.5, 0.5 plus J.2. I'm going to leave it at 0.2, J.2. Now, that's the impedance domain. Hear me? All right, we got a real part that's less than 1 here. Now, listen. If we add impedance in series, y'all see if this is the point right there, I can go this way, right? And I can get to this point, or I can go this way and get to this point. Because once I'm at that point, then I go to the other domain. If that's impedance, then I go to admittance and add something, and voila, and it's done. Now follow the technique. We were trying to get impedance matching by get that back to this point, by adding elements. So remember impedance. If we wanted to go this way, what would we add in the impedance domain in terms of an element? What has a positive J impedance? Inductor. J omega L, right, is the impedance, right? We want to add positive here. Now, what I need from you guys, we'll destroy the tape afterward. Right here, you got to tell me what that value is. The real part is 0.5. Where does this intersect? Look at 0.5 plus J.2. Hop on that line and tell me where the 0.5 intersects there. I can't. You got your tablet. One thing I love about this, you can blow up the Smith charts on your thing so you can really look at. Pardon me? Anybody confirm that? Is it J.46? I just need somebody a second. Or just tell me what you get. That should be 0.5 plus J. Huh?
It's like 0.5 in that book.
No, well, I don't want that book. I want to. What'd you get? You guys got 0.5? All right, 0.5 it is. Plus J, 0. I don't know, but I think that's right. Now, how much did I add there in series? Just do the math on this. I started at 0.2, right? I went to 0.5. I added 0.3. Agreed? And I'm going to say this is just normalized. I'm going to leave it Z0 equal to 100, but I'm just going to say the normalized value of ZL was equal to 0.5 plus J 0.2. So I've just started there, and I don't care what the load is to get there. And it looks like it's going to be actually, 50 plus J 20 would be the actual load. All right, now the first element I have is in series. It's going to be an inductor, and I know the impedance of this thing normalized is going to be equal to you had to get to 0.5, so it's J 0.3. Do you agree? Now that's normalized. And this is another way to think about it. Yeah? Go ahead.
Why can't we subtract off J 0.2 and just add a resistor series?
Why can't we subtract this off and add a resistor, right? Good question. Anybody want to answer it? It's a straightforward answer. What's bad about a resistor? They absorb power. All right, we don't want any power loss. All right, you never add anything that's going to cost power, because that's the whole idea, is to never have any kind of power loss. But you're absolutely right. That would do the job for impedance matching. The problem is it would at the price of power. All right, now we're there, right there. And now I've got a value here in the impedance domain. Could you do this for me? So this is going to be the normalized impedance right there is equal to that at this point. Take 1 over that, and now we're going to get to this point. This was 0.1. This was 0.2. Now we're going to go to 0.3, and I need the value of this. It'll be 1 about minus J something. You're going to have to, what is 0.5 plus J 0.5, 1 over? Is that 1 minus J1?
Yeah. Yep.
Man, that's a great number. 1 minus J1. With me? This is a bad design. If I've got minus J1, no, it isn't actually. Let's take it back. The capacitor is going to be in parallel. All right, now this is the admittance domain, right? Right? We started at impedance, ended at admittance. I've got to add what to get to the 1 circle to it? Plus J1, right? And it's admittance, so it's in parallel. So what I'm going to do right here is going to put a capacitor here that's going to have an impedance of plus, this is going to be an normalized admittance of plus J1 right there. This is going to have a normalized impedance of plus J3. Do you all see this? Now your impedance matched. Remember, at this point and this point. But this is a Y, and this is a Z normalized unit. We're going to get the actual values. Are you with me? Please be careful I know it's very easy to say, oh, I got this. And then come test time or quiz time, you get all confused. So realize the thought process. We're trying to get to the center, and in doing so, we have to find a path that works. And it depends on whether you're in the rotated or non-rotated circle so far. So for this one, if that's 0.3 and that's an impedance, what value would it be? Well, think about this. If it's J 0.3, first take the impedance of an inductor. You know it's going to be an inductor, right? Well, the impedance is J omega L. That's the impedance, but it's normalized, so you divide it by Z0. This is the way you aren't going to mess up if you do it this way. Now, if that's the impedance, and I want the value of L, what can I see happening? If I want L, I take 0.3, right? And then I multiply it by Z0, and I divide it by omega, and I have L. Agreed? All right? Whatever value. It doesn't matter at this point. How do I get this value? Remember, that's normalized capacitive admittance, right? Capacitive, the impedance of a capacitor is 1 over j omega c, correct? If I normalize the impedance, it's 1 over j omega c z naught. The normalized admittance would be j omega c z naught. So the normalized admittance would be j omega c z naught, and that would be equal to j1. Follow me on this, class? Because that's what we want, is plus j1 there, right? It's in parallel, it's an admittance. Can everybody see this? I'm doing my best here, guys. I'm doing my best. Okay, now, what's that value going to be? Well, C here would be equal to what? 1 over omega z naught. Do you agree? And that's how you do this if the load, if the normalized impedance is inside the rotated circle. And if this makes logical sense to you, you will not mess it up on a test, because you won't be panicking thinking, oh, what happened? I forgot if I do A, B, C, because it would make logical sense. This is the only logical way to get to the center. Now, there's another case, and that's if the normalized impedance is outside both of these circles. If it's somewhere outside, we're going to do this one. This one's the easiest because you can do anything you want. And I'll show you what I mean by that. I say that loosely, but it's true. You have the most flexibility. Has anybody ever done this before? You've done impedance matching, right? Yeah. Where it was just locating stubs and links to stubs. But here, remember, what we're trying to do is minimize the footprint or minimize the usage of that board, the Duroid board. So we want itsy-bitsy elements. And these things, to tell you the truth, I don't think I've ever packed any of these things really thick with stuff, but you know, normally you're going to have amplifiers. You'll have standard operational, high-frequency operational amplifiers. You're going to have a power transistor. You're going to have some connections to the outside on these boards. Usually it's coax cable, 50 ohm to 75 ohm cable. You're going to have power supplies. And you're going to have a bunch of other things. If it's a signal processing type of thing, like if it's a radar front end, then you're going to have a whole bunch of DSP stuff there. And where there's a lot of sampling and the reconstruction. And there's a whole lot of lines running everywhere on these boards. But the idea is that they're super densely packed. And you try, I'm not seeing these multi-level ones, but I know sometimes they'll stack boards on top of each other. The problem with that always is the coupling between the lower board and the top board. It can be vicious, so they usually have to put a piece of metal between them to prevent that kind of a coupling problem. All right, now the third case, or part C, it's where ZL, the normalized impedance, is outside either circle, either of these things. All right? In that case, now we have this. I'll just pick a value. All right, and some of you are probably, I see people cramming for the quiz and stuff like this. I tried to print that thing out. Daniel Geiger was printing a million things, and he said he'd bring it down. It didn't print, so we'll do it on Monday. Unless somebody's, if you're bound set on having it today, then I'll go get it. But is Monday all right?
Yes.
All right, and hopefully it'll print out today. So now, follow me on this one. By the way, is anybody going to see the LSU Alabama game? How did you get tickets for that?
My buddy's dad,
Oh, never mind. All right. So you didn't get him a Ticketmaster or anything, right? Do you see what those prices are? $400, $500.
You saw the president's going?
Yeah, I know, but he doesn't have to worry about ticket prices. I do. I want to see that game, actually. All right, off the record. And don't get me in trouble. I'm hoping LSU wins, but I know it would be best for us if Alabama won, right? Well, yeah, because if Alabama won and we beat Bama, then guess what? We may get a shot. But deep down inside, I can't root for Alabama. It's an impossibility. I don't think I can get in too much trouble for saying that in an Auburn classroom. If I get fired for that one, they got problems. All right, Now we're going to be outside either of them. By the way, when you come back, I want to ask you some questions about that game because Alabama, did they say they sell alcohol in that stadium? Anybody been in there lately? Half of the SEC sells alcohol now. I don't know. It's probably $500 for a cup or something, but they sell beer and wine in the concessions. We're about to do it next year. We're taking a look at everything. If you're going, right? I don't. Does Alabama sell alcohol? They don't? Never mind. Scratch that. So for this one, we're going to find a value. We're going to say the normalized is out here. Listen, guys. Here's the one thing, right? This is J1 here, and that looks like this. Now, I'm going to pick a target value. I know this is the one circle. So if I'm at something like, I don't know, 0.7 right here, right, 0.7 plus J1, it would be about here. Take a look and see it, 0.7 plus J1. So that's my normalized impedance. Y'all see it? I want you to just take a look. You all see that right there? Now, huh?
What's that line you got?
I'm trying to estimate where 0.7 would be for the real part. So this would be like, and that's a loose drawing there, but it's 0.7 is the real part. Do you follow me? So if you hop on 0.7, where it intersects J1, that's my starting point. Now here's what's cool about this. You can't mess this one up. I'm in the impedance domain originally, right? Listen. If I add impedance to go to this circle right here, right, that's going to be a positive J. Let's see, sorry, that's negative. I'm going to take it from J1 to J like 0.5, something like that, right? So I'm actually subtracting an impedance, which would be a capacitor, right? Class, you all see this? And we'll do it. I could go here. Now I'm on the rim. Then I go from the impedance domain to the admittance domain, and now I could add another admittance that would get me back here. These would be two capacitors. Do you all follow me on this, class? Or I could go from here and go right to the admittance domain, right? And then I could add admittance to get to this rim right here, and then jump back here in the impedance domain. So you can do either a parallel and a series, parallel first, series next, or a series parallel. Either one will get you there. Now somebody's going to say, can you have two parallel? No. Can you have two series? No. It's always one's parallel in shunt, the other's in series. Follow me, class? I want to do this one for you. I mean, we can do this together. Please, if you have access to those Smith charts, just work with me on this one. It'll make it real to you. I'm staying in the impedance domain for the first part. Now, I have an impedance of this is 0.7 plus J1. I stay on the 0.7 line, and where it intersects this circle, give me the value right there. It's a J.4 something, maybe 0.5, maybe 0.3. Can you all see this right here? J.7 intersects that circle. Hop on that if you can. Y'all, I know you got phones, but that won't work too well for looking at this. Can you all see it? No, just give me your eyes are better than mine. What did you get for this? The J part? Get on the 0.8 circle, or the 0.7 circle. The real part is 0.7, and it hits right in there somewhere. Anybody confirm that? Yeah. 0.46? You get that? Okay. So this is going to be, this point is going to be Z equals 0.7 plus J 0.46. Now what's the difference? I went from J.1 or J1 to J.46, which means I need to add a negative impedance, right? A capacitor, correct, class? It's got a value of what? 0.54 minus J.54. So this is going to be a series element. And actually, it's going to be a capacitor. I might as well put it in there. And this has a normalized impedance of Z normalized equals minus J 0.54. I got 0.54 by taking 1 minus 0.46. Got me? How many see this right here? Guys, do you understand this or not? Allie? Okay. Now, what am I going to do now? I'm at this point, and I'm right on the rim, right? And this should be the value. If I take 1 over this, I'm going to be on the rim here of the non-rotated circle. And it better have a value of about 1 minus j something. So this is 0.1 right here. This is 0.2, and this is 0.3. What do you get for this value? We'll get the values of the capacitors in a second.
Minus J 0.656.
Agree? Now, that is the admittance domain, correct, class? Admittance domain, and we want to add a positive J admittance to get rid of that, correct? What's that going to be? Capacitor, right? So we got a capacitor there. We're going to have another capacitor here. And this capacitor is going to have a admittance, normalized admittance, and I guess you could call it Y normalized, of plus J 0.656, right? 656, something like that. All right, now the values. Keep in mind, you got to, if it's in series, it's impedance. Up here, a negative impedance means a capacitor, right? So that means this is equal to minus j over omega c z naught. Or the value of c for that one would be what? C would be equal to 1 over 0.54 times omega times z naught. And that would be the value of that capacitor. Call it C1. Agreed, class? I want to finish this up. Everybody got that? Now what about this capacitor right here? That's admittance, correct, class? For admittance, what would this be? Well, admittance is 1 over normalized impedance, right? So instead of having minus j over omega c z naught, it would be j times omega c z naught. So this is going to be equal to j omega c z naught, or in this case, C2. The one in parallel would be equal to 0.656 over omega and z naught. And that will get you there. I'm going to give you problems with this. I posted that Smith chart so you can print it out and do them. I suppose there's actually tools now so you could literally work on a Smith chart right on your tablet. I don't have that tool available. There are some tools, some JavaScripting tools that do this. But if you print them off and get your compass and a straight edge, you can see that this does work. And this is commonly used. So this is not some technique that's like antiquated. We really do this for a lot of stuff. Y'all understand what we're going after? I'll give you some homework. And on Monday, I'll give you a quiz. And the quiz will be on the common mode chokes. And I'm sorry that the thing, I didn't know Daniel Geiger had that thing locked up for 30 minutes. All right. I still want to hear about the game. I don't know how after you get back on Monday.